Hello, today we're going to talk about atomic structure and electron configurations. So let's start by reviewing a few basics. The nucleus will have protons and neutrons, and then around the outside of the nucleus is where the electrons will be. Protons are positive, neutrons are neutral, and electrons are negative. So on the periodic table, let's consider carbon. You'll have the atomic mass, the atomic number. Atomic mass is a weighted average, and atomic number tells you the number of protons. The mass number and the number of neutrons are not included on the periodic table typically. Now, if your atom is neutral in charge overall, then you'll have equal numbers of protons and electrons. So if you have a neutral carbon atom, you would have 6 protons and 6 electrons. If you have an atom of carbon-12, where the mass number is 12, that means you have neutrons of 6 as well, because protons plus neutrons gives us the mass number. You could also have a carbon-14 atom. A carbon-14 would have 8 neutrons, because in this case, again, when you add up the protons and neutrons, you get 14 as your mass number. Now, you can also have a charged particle. If it has a charge, then it is called an ion. Carbon doesn't like to form ions as much. Let's think about oxygen for a second. Oxygen has 8 protons. So in a neutral atom of oxygen, there are 8 electrons. But sometimes oxygen gains 2 electrons. So if it'll have 8 protons and 10 electrons. In that case, I have more negatives than positive, so oxygen has a charge of -2. So it is a negatively charged ion, it is an anion. You can also form positively charged ions. Those are called cations, and that's when you have more protons than electrons. Remember, an atom will keep the same number of protons to keep its identity. So the number of protons will only change if you do like a nuclear reaction, which is not really covered on the AP chemistry exam, but the electrons could change. You could gain electrons or lose electrons, depending on the reaction. Let's also go over how to do Bohr models. They're not necessarily the perfect example of a model for atoms, especially knowing what we know now about atomic structure. However, they can be really useful for showing the first couple of energy levels. So when you're drawing a Bohr model, you would draw just like a dot for the nucleus. Bohr said that there, 2 electrons would go in the first level closest to the nucleus. The second level could hold up to 8. And then the third level could hold up to 8. After that, it really gets not very useful to draw Bohr models at all, so I'm not going to draw it any bigger. But just note, each of these are considered energy levels. The lowest energy state is closer to the nucleus. Higher energy state is further away from the nucleus. So those are Bohr models. I don't know if you noticed, but I drew, 1 electron on each side before doubling up. That's to make it really similar to Lewis diagrams, and we're going to get to Lewis diagrams in the next unit. But for now, Bohr models 2, 8, and 8 for those first 3 energy levels. So like I said, Bohr models aren't really the perfect way to imagine an atom in real life. Bohr models are just useful sometimes for quickly and easily drawing electrons around the center nucleus. In reality, the electrons travel in things called orbitals. Orbitals are 3D shapes. They're like spaces in which the electrons can travel. So there are 4 shapes of orbitals. So we have S, P, D, and F. S is a sphere. Okay, now I'm drawing it and it's flat, but imagine it's 3-dimensional, it's a sphere, and the electrons can move anywhere inside that sphere. It's not like they're rotating around the outside. P orbitals are shaped like dumbbells. It actually kind of looks like 2 balloons stuck together, but we call them dumbbells. And there are 3 possible P orbitals for a sublevel. But they would be facing different directions. So you might have a vertical, you might have a horizontal, And then you might have, if you imagine it in 3D, imagine, one orbital coming toward you and one orbital facing away from you. I'm sorry, one side of the orbital coming toward you and one side of the orbital going away from you. That would look, I'm just going to draw it at an angle, but it's because it's hard to do in 3D. But you can picture it almost as like this is on the y-axis, the x-axis, and then the z-axis coming toward you and away from you. So S is sphere, P are these dumbbells, and again the electrons can move anywhere in those dumbbells randomly. They do not have to follow around the outside. It's not like it's doing a figure eight. They're 3D spaces where the electrons move. D are these flowers, and don't worry, you won't be asked to draw these, but there's flowers, and again they're going to be facing in different directions, but there will be 4 flowers in a sublevel, and then what I call a dumbbell donut. I don't know if anybody else calls it a dumbbell donut, but it's basically a dumbbell with a donut-shaped ring around the center of it, and there's one of those. So right now we have 1 s orbital, 3 p orbitals, and 5 d orbitals. F is just like these crazy bunch of balloons, and I'm not going to draw it, and you won't have to either, but just know that there's 7 of them, so 7 of those different shapes. But yeah, so they're the shapes, the 3D spaces in which the electrons travel. So now let's connect the Bohr model to the orbitals. So Bohr models, we talked about there's, energy levels, and the lowest energy is close to the nucleus, and then as you move further away from the nucleus, you get higher energy. And that first energy level can hold up to 2 electrons. So that first energy level translates to 1 s orbital. So we have an s orbital, which we call the 1s orbital because it's the first energy level is close to the nucleus and it's a sphere shape. The second energy level, according to Bohr, had 8 electrons. Okay. So it's a little higher energy, and there's 8 electrons, but what that looks like is you have an s orbital, and you have 3 p orbitals, so those 3 dumbbells. I'm going to draw them facing the same direction, but remember they're in the XYZ planes. So this would be, all of these are p. But we were going to call this a 2s and a 2p because it's further away from the nucleus. It's in that second energy level. And each one of those can hold 2 electrons total. So you wind up with 8 electrons total because there's 4 shapes. So 1, 2, 3, 4, 5, 6, 7, 8. And again, they can move anywhere within that 3D shape. So like this 1 electron isn't confined to that end of the orbital, but it's just nice to illustrate it that way. So you wind up with 8 electrons in that second energy level. And then the same sort of holds true for the third one. You have a 3s and a 3p. But past that, it starts getting a little funky. And we'll talk about that as well. But you do need to know that they fill in from the lowest energy first. So they start in the 1s, those 2 electrons in that 1s sphere. And then a little bit further from the nucleus, you have 2s. The sphere, 2 electrons. A little bit further is those 2p dumbbells. So you're getting up to the 8 total. And then you'd have 3s and then 3p. So that brings us to a total of what, 18, right? Yeah, 18 electrons. And then past there it starts getting a little wonky, and we will talk about that. Now if you were to imagine this all overlapping in a single atom, because that's what it does, is so imagine you have this teeny tiny sphere, the 1s sphere, and then the 2s sphere is a bit bigger, and then you have your 2p orbitals. So these are dumbbells, but they're a little bit bigger because they're a little higher energy, a little further away from the nucleus. And then you have a 3s, which is a sphere again, and then you have a 3p, which again is a little bit bigger, but it's still those dumbbell shapes. And so it starts looking very strange, but don't worry, you don't have to be able to draw this ever. So what about those d and f orbitals? So let's talk about those a little bit. I'm going to move this over to 3p. So we have, in the first energy level, we only have s. Second energy level, we have an s and 3p's. In the third energy level, we have an S, we have 3 P's, and we have 5 D's. In the fourth energy level, we have an S, we have 3 P's, we have 5 D's, and we have 7 F's. So do you see the 1, 3, 5, 7 pattern for the SPDF? And then we have the 5th and 6th and 7th energy levels as well, which we'll look at when we look at the periodic table. But yeah, so again, these shapes repeat just larger and larger as it's getting further away from the nucleus and more energy. Now, there's 3 main rules for electron configurations. We already talked about one of them. You always go from lowest energy to highest energy. So that means you're starting closest to the nucleus with a 1s sphere and working your way out as you add more and more electrons. The second rule is that you can only have 2 electrons per orbital, and they have to have 1 of each spin. So electrons have a spin, clockwise, counterclockwise, if you want to think of it that way, although it's in 3D space. If one is spinning one way, the other is spinning the opposite way. And so we'll use arrows to represent electrons sometimes to show that they're the opposite spin. So in an s orbital, you'll have 1 up and 1 down. And then the last rule is called Huns Rule. And Huns Rule is important when you have multiple orbitals of the same shape. So all those orbitals are p orbitals. They're all dumbbells. Okay. And let's say they're all dumbbells from that second energy level. So they're all 2p orbitals. We call the 3 of those orbitals together, we call that a sublevel. And Huns Rule is important just in those cases. So you'll never have to use Huns Rule with s, because there's only ever 1 s orbital. But you'll have to worry about it for p, d, and f. With P, D, and F, you have to make sure they're going to put 1 up arrow or 1 up spin electron in each of those orbitals before you double up. And that's because the electrons repel each other, because electrons are all negative. The like charges repel each other. So they spread out as much as possible before you would double up. Now, a lot of times we don't actually draw those dumbbell or sphere or whatever shapes. So we'll use boxes just to make our lives easier. So you'll have 3 boxes to represent the 2p sublevel, and you'll put 1 arrow in each before you double up. And it's convention that we always put an up spin in each of those sublevels before you put a down spin. And again, this is as you add each additional electron to the atom. Okay, so how do we know what order they go in? If you have to go from the lowest energy to the highest energy, you don't have to memorize it. So you can number the periods 1 through 7 on the periodic table. 1, 2, 3, 4, 5, 6, 7. And then the first 2 groups, columns on the periodic table, are the S block. These ones are the P block. The transition metals in the center, that's the D block. And then the lanthanides and actinides, which are the inner transition metals, those would be the F block. Okay, so now how do we use that? So you always go in order from the very first element, so hydrogen, and you work your way up to the element that you're working on. So if you're starting at hydrogen, this would be the first period, and it's in the S block, so 1s comes first. And then this particular image moved helium over here just so that it's with the S. Helium's the only kind of weird one. Sometimes we group it with the noble gases on the end. Sometimes we group it over here so that it's with its orbital group. But yeah, so you would do 1s and you would fill 1s first. And we fill electrons using exponents, right? So S can hold up to 2 electrons total. Then still going in order after helium, the next element is lithium. So you'd go over here, 2s would be next. Then 2p, and again, as you're adding each electron, it would go into that 2p. So 2s to 2p6. After 2s, you would come into 3s, 3s2, 3p6, because you're going straight across. And after 3p, you'd go over here to 4s and 4s2. Now this is weird, the transition metals get funky. When you go into the D block, you kind of go backwards. D starts with 3. You start numbering D with 3. So after 4s comes 3d, and D can hold up to 10. But then it goes right back up to P, 4p, up to 6. And then 5s2, 4d, excuse me, 4d, 10, 5p6. When you get to the next level, 6s1, but then that's where the lanthanides and actinides jump in. So, sorry, 6s2. So then you'd have 4f. F can hold up to 14. So 4f14, and then you go back to the D block, 5d, 10, 6p6. And then your last period, 7s2. This has a typo. This should be 5f. And so then 5f14. 6d up to 10. It does go all the way up to 10, and then 7p6. You would round that out. So that's how you can use the periodic table to remember the order of these orbitals. You could memorize them if you want to, but I think that's kind of a little extra. S block, P block, D block, F block, and then you start numbering them. Start the S block at 1. The P block starts at 2, D block starts at 3, F block starts at 4. 1, 2, 3, 4. There is no such thing as a 1P. There's no such thing as a 2D. There's no such thing as a 3F. So always use a periodic table as your friend. Okay, so you might be asked to draw an orbital diagram, or fill in an orbital diagram, or look at an orbital diagram. All that means is that we're using a box to represent one of those shapes. So instead of a sphere or dumbbell, we'll draw a box. But again, you always start at the lowest energy, which is 1s, and you'd fill in an electron, a second electron. Let's go ahead and do oxygen. Oxygen has 8 electrons in a normal oxygen atom, neutral oxygen atom. So you always start 1s. Those are the first 2 electrons. Then the next one out would be 2s. And you fill that in. And then after 2s comes 2p. And we always draw 3 boxes for p because there's 3 dumbbells. So this is the 2p sublevel with 3 boxes. Now we have 1, 2, 3, 4 electrons so far. We need 4 more electrons to make oxygen. So you do 1, 2, 3, 1 in each. That's Huns Rule. And then the 4th one you would fill in as a down arrow. And so this is the orbital diagram for oxygen with those 8 electrons represented as arrows. Let's do another one. Let's do neon. Neon has 10 electrons. 10 electrons. So again, you start with 1s. You do up, down. Then comes 2s, up, down. 2p has 3 boxes because it's p. And so then 10 electrons total. We already have 4, 5, 6, 7, 8, 9, 10. Do you notice how that's completely all filled up? Everything is good and stable. That's part of why neon is one of those noble gases. Full stable orbitals. And then you can just go in order. If you ever get to the D, you would draw 5 boxes for D. Because of those like 5 different d orbitals. I've never seen them ask for F, but if there were, you would draw 7 boxes to fit those 14 electrons for F. Okay, so let's go back to oxygen. It's 1s, 2s, 2p, and we have our 8 electrons in the oxygen atom. So that's oxygen. Now, drawing boxes and arrows every time gets really annoying, and chemists are lazy, so we'll do the shorthand notation, which is 1s2, because there's 2 arrows in the 1x box, or 2 electrons in the 1s orbital. 2s2, 2p4, because there's 4 arrows in that 2p sublevel. When you're doing a shorthand notation, you just go ahead and you group all of those p electrons together, even though they're in separate orbitals. Neon, the same way. You would do 1s2, 2s2, 2p6. Most of the time when they're asking you for an electron configuration, I'll even write that out, electron configuration, this is what they mean. This is what they're looking for. They'll specifically say an orbital diagram if they want you to draw the boxes and arrows, but most of the time they want this, which is it tells you the energy level, which is the number, the shape of the orbital, which is the SPD or F, and the number of electrons in that sublevel, which is the exponent. Okay, the last thing for this section is noble gas notation. So we talked about neon having that perfect noble gas notation. That perfect noble gas configuration where it's completely full. All of its orbitals, energy levels were full of electrons. That makes it very stable. So if you have a different element, one that's not a noble gas, you can use what's called noble gas notation. The noble gases are here, including helium. But what we can do is take like a really big element and take its electron configuration and make it much, much shorter. So let me give you a couple examples of that. Let's look at, let's do aluminum. Aluminum has 13 electrons. So 1s2, 2s2, 2p6, 3s2, 3p1. Okay, it's right here, 3p1. The noble gas that comes before aluminum is neon, which we looked at. Neon has just this part. Okay, if you cut it off here, this would be neon's electron configuration. So when we're writing noble gas notation, you can write just that noble gas in brackets and then write everything that comes after, just the 3s2, 3p1. So this is the noble gas notation for aluminum. But it gets really useful when you get the really, really big ones. So let's do something like, iodine. Iodine has 53 electrons. So if I'm going to do that, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p7. I'm sorry, 5p5, my bad. Okay, so those are 53. So iodine's right here, 5p5. So the noble gas that comes before iodine, just before iodine, is this one here. That's krypton. Krypton has 36 electrons. So the first 36, you don't have to write. You can just write Kr for krypton. And then you would just write everything that comes after it, the 5s2, 4d10, 5p5. And so this would be the noble gas notation for iodine.